Hi all. In this video we're going to talk about sample variance. We've been talking about population variance and population standard deviation. But what do we do when we have a sample? We have to figure variance in a different way when we're dealing with a sample as opposed to the total known population. So in this video I'm going to review why we use samples. We're going to talk about sample variance and something called degrees of freedom, and then we'll talk about sample standard deviation in the next video. So, as a reminder, inferential statistics uses limited information from a sample to generalize to a larger population. And when we do that, we assume that our samples are representative of the population. We've talked about that. They should be very similar to the population, if not exact. But this is a problem with variability when we draw a sample. So why is it a problem? It's a problem because when we have a sample, it will tend to have less variability than the population. Let's recall that extreme scores can create larger variability and clustered scores create smaller variability. When we're dealing with the actual population, we have a greater chance of having extreme scores. There's more possible people, more possible scores. And so populations have more variability usually than do samples. So if we were just to take the variance of a sample and apply it to a population, that would be a biased estimate of population variability because we would be underestimating the population value. And in doing so, we would be losing some accuracy. So we have to make a little bit of an adjustment when we're talking about sample variance. And we do this so that we can make an accurate and unbiased representation of the population variance. We want it to be reflective of the population. So what is this adjustment? Well, it's simple. When you're doing your variance formula for a population, we've been calculating sums of squares divided by n. But in this case, we're going to take the sums of squares and divide by n minus 1. N minus 1 is the small adjustment that we make in order to have the variance that we're seeing in our sample reflect what's probably happening in the population. And we call this n minus 1 by a statistical name, degrees of freedom. You're going to want to write down degrees of freedom. I'm going to talk with you about what they are sort of on a conceptual level, but then I'm also going to talk to you about what I really want you to remember about degrees of freedom. So for any sample of scores, n scores, that could be 5 scores, 10 scores, 15 scores, the degrees of freedom, or the DF, for the sample variance, the denominator in the variance formula, is defined as n minus 1. I just said that in the last slide, but n minus 1 is our denominator, and it's called degrees of freedom. So degrees of freedom determine the number of scores in a sample that are independent and free to vary. So what does that mean? Well, part of this is knowing the mean set of a set of scores places a restriction on the variability of the scores. So let's look at an example. This will probably help more. Let's say we have an n of 3 scores and the mean of all those scores is 5. So I know that means that the total of all of the scores is 15. So just think of it this way. If there are 3 different people and they each have a slice of 5, that means that adding up all those scores would be 15. So I'm going to come over here to the right and say, what is the third score in this case? We have 9 and we have 2. So that question mark score has to be a certain number. It cannot be any other number but this one number. So what is that one number? Well, that one number is 4. Because we had 9 plus 2 is 11, and we know the total is 15, so that last score is determined. In other words, it can't be anything else. Now let me just say what it means to vary. So I could have had these two scores be 7 and 4, or I could have had these two scores be 5 and 6. And whatever these two scores were, they could be anything in the world. But when you know these two scores, the final score is determined. It can't be anything but the score that's needed to make the mean of 5. So let's take a look again. So 2 of the 3 values in this example can vary, But the final score depends on the values of the first two. So like I said, I could have 9 and 2, I could have 6 and 5, I could have all sorts of configurations. But once I know those two numbers, the last number has to be a certain number. So with a sample of however many scores, the first n-1 scores are free to vary, but the final score is restricted. So let's say we have a sample of 15 scores. So that means the first 15 minus 1 scores, or 14 scores, are free to vary, but the final score is restricted. I know this is a little bit heady, and a little conceptual. As a result, the sample is said to have n-1 degrees of freedom. And the restriction on this last score is there because of the mean, because we know that we're looking for a mean, and that mean is determined, that mean is 5, so that last score can't vary based on what the other two scores are. It's committed, it has to be what it is. So here again is the formula for sample variance, and you'll notice that we have a new symbol for sample variance. Our symbol for population variance was sigma squared, but for sample variance, it's a lowercase s squared. And again, the formula is not sums of squares divided by n, but rather sums of squares divided by n-1, or sums of squares divided by the degrees of freedom. So how do I interpret this sample variance? It's the average squared deviations for a sample of scores or values. Remember, we're talking about squared deviations with variance. But what I like to say is this is an estimation of the population variance, because this is not the actual variance of the sample, because we're using n-1, but rather we're saying that this is an estimation of what the population variance would be based on this little sample that we have right in front of us. Okay, so what do I want you to remember? I said I would tell you this. I want you to remember that when we are talking about sample variance, you're going to have n-1 in the denominator as opposed to n. We use a different symbol for sample variance. Instead of sigma squared, we have s squared. And sometimes we call n-1 degrees of freedom. These are interchangeable for this variance formula. And finally, what I'd like you to remember is that when we're calculating sample variance, it's really an estimate of what the population variance would be. So I hope this makes good sense to you. In the next video, we're going to talk about sample standard deviation, and then we're going to put some things together with practice.